So, just to summarize, I will put down all the steps, right. So, spectral clustering at scale right. So, the input is just the data set, and then we want to cluster this into k clusters, let us say, and let us say we have some k as input. First part would be to compute G, which is the original graph. Now, and compute what is G? G is V comma E comma W, that is given to us. Compute R effective approximately for all ij in E. Once you have computed effective resistances, sample using Pij proportional to R effective. I will put a hat to indicate it is an approximate R effective of Ij to create H. Now, compute LH, use sparse eigenvector solver to obtain, let us say, f1 till fk corresponding to lambda 1 less than lambda 2 less than or equal to lambda k. These are the eigenvectors. And now normalize rows of f, which has columns f1, f2 till fk. We are normalizing the rows, and finally, run k means on the embeddings. Normalize the rows to get embeddings basically. To get final clusters. Of course, k-means can be run using good initializations using k-means plus plus and so on. So, all that stays, right. So, because k-means is crucially dependent on initialization. So, if you are aware of k-means plus plus, that is a probabilistic way to initialize k-means, right. So, you can use such techniques also to run k-means. But then for us, I mean, that's just a black box that we are using. The key point here, for to run spectral clustering at scale is, first of all, we have to compute effective resistances approximately, and the key thing is that you sample using Pij to create H, and H, remember when I say H, it is not just H has V, F, W prime, and then you scale the weights, right. So, and that is very important, because otherwise in expectation this is not going to be the same, and so these high probability bounds will not kick in. And now then you compute the Laplacian and do the usual business from then on, right. So, after you compute H, everything else is the same, right. So, it is the standard spectral clustering, but then apply to H the sparser version of G, and the hope is that this is going to give you much better clustering than just doing a sparsification by taking a k nearest neighbor graph, because that we do not know if it is going to preserve your cuts necessarily, whereas here an approximate version of the cuts will be preserved, and so hopefully the clustering is going to be better. So, that is how we would do spectral clustering at scale, and this kind of ends our discussion on spectral clustering and then doing it using randomization and posing it as a linear algebra problem, then standard using randomization. So, and this ends this part of this course. Next time we will look at some other algorithm for data science and see how other techniques that we have learned come into use. Thank you.